Hi friends, welcome back to our channel Physics Tutorial. Today we are going to continue with the plus 2 physics, that is electrostatic potential and capacitance. In the last class we had discussed the potential energy of electric dipole in an external field and electrostatics of conductors. Hope it was clear to you, and now we can move to the next topic, dielectrics and polarization. Are you ready? Here we have to study about dielectrics and then polarization. Okay, so what are dielectrics? Dielectrics are actually insulators. That means that are non-conducting materials. That means they will not conduct electricity, but it will allow the electric field to pass through that. Okay, so some insulators like paper, mica or air, all these are dielectrics. Okay, and not like conductors, the dielectrics are classified into two. That means there are polar molecules and non-polar molecules that we have already discussed in the first chapter, right? So polar molecules and non-polar molecules are two types of dielectrics. Okay, so this type of dielectrics will be made up of polar molecules, and the non-polar molecules means it will be that type of dielectrics will be made up of non-polar molecules. So we can just see that what is polar molecules and then what are non-polar molecules. Here we can see in the case of polar molecules, the centers of positive and negative charges do not coincide. That means if you are taking a charge like this, here we can see positive and negative charges will be here, right? So here this positive and negative charges will not coincide each other. So here there will be a separation between these two charges. That means there will be a permanent dipole moment. So that is the peculiarity of polar molecules. So in the case of polar molecules, the positive and negative centers of charges are not in contact. That means there will be a distance between these positive and negative charges. That means there will be a permanent dipole moment. That is very important. There will be a permanent dipole moment in the case of polar molecules. And in the some examples for polar molecules are HCl, H2O, etc. Clear? So when we talk about polar molecules, you have to remember that the positive and negative charges should not be coinciding, and the examples are HCl and H2O. It has a permanent dipole moment. Now, what are non-polar molecules? So in the case of non-polar molecules, the centers of positive and negative charges will be coinciding. So what will happen here? Suppose we are taking like this, the positive and negative charges will be together. Alright, there will be no distance between these two charges. That means there will be no permanent dipole moment of its own. So that is the difference between this polar and non-polar molecules. Some examples are oxygen, then H2O, H2, like that. Okay, O2, H2. All these are examples for non-polar molecules. Okay, so this is all about polar and non-polar molecules. Now we can consider this polar molecule and non-polar molecule. If you are placing this in an external electric field, what will happen to them? So that we are going to discuss. Here we have to consider a non-polar molecule, and if you are placing that non-polar molecule in an external electric field, what will happen here? Here we can see the electric field is 0. That means it is not placed in an electric field. In such a case, the positive and negative charges are coinciding. Right, here there is no difference between these positive and negative charges. That means there will be no permanent dipole moment of its own. Right, now we are placing this non-polar molecule in an external electric field. Here external electric field is there, and in such a case what will happen? Here we can see this positive and negative charges will be moving to both sides, right? That will align in the direction of electric field. Then what happens is that in this side, here we can see positive charges are here. Right, all these positive charges are here, and here negative charges are there, and this negative and positive, all the other charges in between, they will get cancelled. Right, the rest of the charges, only this positive side is there and negative side is there, and it will make a permanent dipole moment. Okay, so here the charges will get separated and there will be a permanent dipole moment. That means in the case of non-polar molecules, if you are placing that in an external electric field, what will happen? There will be a net permanent dipole moment formed in such a case. Clear? And now we can consider the polar dielectrics. That means polar molecules, if you are placing in an electric field, what will happen here? That means here electric field is not there. That means this is the polar molecule, and if you are placing like this, here we can see the positive and negative charges are separated by a distance. That means there is a dipole moment. But if you are taking the net dipole moment, what we will get here? Here it is randomly arranged. It is not arranged in order. So if you are placing like that, this positive and negative, all these dipole moments will get cancelled. That means there will be no net dipole moment for this polar dielectrics. Clear? And if you are applying an electric field, here electric field we are applying, that is not equal to 0. So what will happen here is these positive and negative charges that will align in an order. Okay, so in such an order, if we are arranging here, we will get the net dipole moment. Here also in the previous case, right, here positive charges are there and the rest of the charges will get cancelled. Okay, positive and negative, and here positive and negative, all these charges will get cancelled, and the remaining charges will be only positive charges in this side and negative charges in opposite side. So net dipole moment will be there, that will not be equal to 0. Clear? That means if you are placing this non-polar molecule and polar molecule in an external electric field, there will be net dipole moment. So that is the case of polar and non-polar molecules. Clear? The next topic is polarization. It is represented as P, and polarization is the dipole moment per unit volume. Polarization means dipole moment per unit volume. And suppose the dipole moment is in the same direction of electric field. That means the induced dipole moment is in the same direction of electric field, and the strength is also proportional to the field. Then we can call it as linear isotropic dielectrics. So in case of linear isotropic dielectrics, the polarization will be proportional to electric field. That means E. P will be proportional to E. So we can write it as P is equal to chi E into E. Chi E is a proportionality constant which is called the electric susceptibility. That is P is equal to chi E into E. This will happen in the case of linear isotropic dielectrics. So P will be equal to chi E into E, and chi E is a constant which is called electric susceptibility. So this equation you have to remember. Okay, and the dipole moment means polarization is the dipole moment per unit volume. Now we can move to capacitor. What are capacitors? Capacitors are actually used to store electrical energy. So electrical energy can be used by using capacitor, and it is a system of two conductors separated by an insulator. So in the case of a capacitor, we can see that there will be two conductors and it will be separated by a insulator. And here we can see that here we can charge a capacitor by using a cell or a battery. Here we have a conductor and this was empty. Now if we connect this to a cell, the charges will be flowing to this side. Okay, so here we can see the charges are flowing here, and here we can earth this thing. Okay, now in such a way we can charge the capacitor, and as the charge increases we can see that the potential also will be increasing. So here we can write it as Q is proportional to V. That means charge will be proportional to potential, and the proportionality constant is C. That is called the capacitance of the capacitor. That means Q is equal to CV, where C is called the capacitance of the capacitor. Then C will be equal to Q by V. Or capacitance, we can the symbol of the capacitor is like this, and this is a variable capacitor. That means we can change the values of the capacitor during an experiment. So this is the symbol of capacitor and this is variable capacitor, and farad is the unit of capacitor. Okay, so farad means 1 coulomb per volt. Coulomb per volt is called 1 farad, and usually we will use the units microfarad, picofarad or nanofarad, like that, small units that we will use. So these points you have to understand. Polarization means dipole moment per unit volume. And in the case of linear isotropic dielectric, the P will be, that means polarization will be proportional to electric field. Then P can be written as chi E into E. This chi E is called electric susceptibility, and that is all about polarization. Now we have capacitor. It is actually a charge storing device, a device used to store electrical energy, and it is a system of two conductors separated by an insulator. And here we can charge the capacitor. That means a conductor can be charged by using a cell, and as the charge increases, the potential also will be increased. That is, Q is proportional to V. Q is equal to CV, and C is the capacitance, and the unit is farad or coulomb per volt. Okay. Microfarad, nanofarad and picofarad are used for the units of capacitors. Okay. Now we can conclude the video. If you like the video, please like, share and subscribe. Thanks for watching.